Good morning, everyone. This is Dr. Sharif El-Gamal, and today we are going to have a lecture about reinforced concrete design. In this lecture, I'm going to talk to you about solid slabs, part 1. It will be introduction to slabs, and we'll concentrate more on one-way solid slabs supported on beams. As you know, reinforced concrete slabs are usually used in floors and roofs of buildings to cover big areas. They carry distributed loads and primarily by bending moments. Of course, there are some shear stresses. It differs from one type of slab to another type of slab. There are different types of slabs you will see. The first type is solid slab supported on beams. And we'll concentrate on this lecture on this type of slabs. In the solid slab supported on beams, you can see that you have a slab, the load will be transferred from the slab to beams, and the beams will transfer the load to the columns. Okay, so you have a slab supported on beams, and the beams will transfer the load to the columns. Another type of slabs that you may also see, flat slabs and flat plates. In flat slabs and flat plates, you will have a slab supported directly on the column without beams. So the difference between the flat slab and flat plates, here in the flat slabs and flat plates, you don't have beams. Loads will be transferred directly from the slab to the column, and in this case, the shear will be effective and will be important. Here you have to take care about the shear because you will have a high shear stresses at the column area. This is why sometimes they make some drop panels around the columns, and sometimes you also use column heads. The third type of slabs, hollow block slabs and ribbed slabs. Hollow block slabs and ribbed slabs. In the hollow block, they use some blocks. It could be lightweight blocks or any type of foam or any other material to reduce the self-weight of the slab. And they arrange these blocks to have a spacing between them. We call them ribs. And in this case, you will have a small slab thickness at the top. This could be 5 centimeters to 7 centimeters usually, supported on ribs here. And the spacing between ribs depends on the size of the blocks that you are using here. In the hollow blocks, you use some blocks or like foams or any other material. In the ribbed slabs, you have only the top slab and the ribs without blocks here. The last type of slabs is called waffle slabs. The waffle slabs have some similarities to the ribbed slabs, but two-way. So it is similar to the ribbed slabs, two-way ribbed slabs. And at the columns, because of the high shear stresses, so you have some solid part. This will be able to resist the higher shear stresses at around the column area. There are different classifications like the spans. You may have simply supported slab or continuous. This is valid for slabs or for beams or for any structure. You may have simply supported or one span only or many spans, or we call them continuous. Also for the supports, sometimes it could be fixed supports or pin supports. And in some cases, you have some slabs with free end, like balconies, you will have a free end, or sometimes you have a slab supported from 2 or 3 sides, and the last side of the slab is free. For the solid slabs supported on beams, which is the topic of our lecture today, there are two main types: one-way solid slabs and two-way solid slabs. What is the difference between one-way and two-way solid slabs? It depends on the geometry. So let's say this is a slab. The long side of the slab here, we call it long span, and the short will be the short span. So if this long span divided by the short span is greater than 2, we classify this as one-way solid slab. If the long span divided by the short span is less than or equals to, even if it is equals, yes. If it is less than or equals to, we'll call this two-way solid slab. Okay, let's see more details about one-way solid slabs. as we said, the longest span divided by the shortest span should be greater than 2. In this case, most of the loads will be transferred in the short direction of the slab. It means it will go to the long column. And in this case, we will assume, if we classified, if the longest span divided by the shortest span greater than 2, we will assume that all the load will be transferred only in the short direction, and no loads will be going in the long direction of the slab. So in this case, if you want to design this slab, you will design only in the short direction of the slab and will not be designing for the long direction. So it means to design for the slab, you take a strip of 1 meter and you get the load on this 1 meter. Of course, the slab here will be supported on this beam, will be like a support. Another long beam here will be another support. And then we'll design this one as a rectangular section of B equals 1 meter, 1000 millimeter, and the H equals the HF, or the H of the slab. So the reinforcement that will we get in this case, it will be the reinforcement in the short direction, or we call it main reinforcement. Okay, how about long direction? Do we need to have reinforcement here? Of course, we need to have reinforcement for shrinkage, for temperature changes, but we are not going to design for this one. We just use the minimum according to the code. So we design only for the short direction, and for the long direction, we just take the minimum according to the code. Okay, in the two-way solid slabs, the difference between long span and the short span is not that big as in the case of one way. The difference, if this long span divided by the short span less than or equals 2, so in this case, the load will be transferred in both directions. Most of the loads will be going to the, or more loads will be going to the short direction, and also some loads will be going to the long direction. So in this case, if you want to design this, you have to design it in both directions. So you have to take a strip in the short direction, get the load, get the moment, and design for that one to get the reinforcement in the short direction. Then you have to repeat again and take a strip in the long direction of 1 meter and get the load on that one, get the moment, and then you design and get the reinforcement in the long direction. So we have to design for the short reinforcement, we have to design for the long reinforcement. What are the design steps? As you know, in this course, we are following the BS code 8110, and we are going to follow section 3.5.1. The design steps, the first thing is we design the slab as a beam. As I told you, we take a strip of 1 meter. So the beam will be assumed as 1000 millimeters. So the design will be as a rectangular section of height equals the H of the slab, and B width of the section equals 1000 millimeter. The first thing after you take 1 meter strip, we start by something called initial proportioning. Because when you design, you don't know how much is the thickness of the slab. What is the H slab? What is the HF? So we need to assume it. Okay, how to make this initial proportioning? We have to start by estimating the effective depth. What is the depth? How to get the depth? We get it from table 3.9, and this is page 215 in the BS8110. And let's go and see what is this table 3.9. This table 3.9, it gives you something called basic span to effective depth ratio for rectangular or flanged beams. And we are going to use this also for slabs, but by adding something called modification factor. What is this one? For the slabs, as you know, the section is a rectangular section. So we have three different types of rectangular section or slabs. It could be simply supported, and the basic span to depth ratio in this case will be equal to 20. If it is a continuous slab, it will be 26. If it is a cantilever, it will be assumed this span to depth ratio is 7. Okay, how to use this one? Okay, to find the depth of the slab, the minimum depth of the slab equals the span divided by this basic span to depth ratio from the table here, multiplied by something called modification factor. And as a guide, you can assume this modification factor as 1.3. But there is something important here. Which span I'm going to use? Because for each slab, you have two spans. You have long span, you have short span. Always the span here that will govern our design and our thickness, it will be the short span, not the long span. So here it will be the short span divided by basic span to depth ratio, even 7 in case of cantilever, 20 in case of simply supported one-way slab, or 26 in case of continuous. And then this modification factor is assumed as 1.3. Just to clarify this, let's see some examples. If you have a simply supported slab of 3.3 times 7 meter, so the dimension of the slab, 3 meters short span times 7 meter long span, and it is simply supported. So how much it will be the effective depth in this case? The effective depth equals the short span, okay, 3,000, divided by basic span to depth ratio. This is simply supported. So in simply supported, the basic span to depth ratio in the table is 20. So it will be 3,000 divided by 20 times the modification factor. Always we assume it 1.3. So it gives us an effective depth of 115.4 millimeter. Another example, if you have a continuous slab of 5 times 7 meters, okay. So again, how much it will be the depth or the effective depth? Okay, again, we are going to apply this equation. The D equals the short span. In this case, the short span is 5,000 divided by basic span to depth ratio. In this case, because it is continuous, so from the table, it is 26 times the modification factor. Always take it as 1.3, so it gives us 147. And again, if you have a cantilever of 1.3 times 7 meter and the span is 1.3 meter, so again, the depth equals the span, but you put it in millimeter to get the depth as in millimeter, divided by basic span to depth ratio. In this case, for a cantilever is 7 times the modification factor, and you have a value of 142.9 millimeter. Okay. This is the first step to estimate the effective depth. Why it is important? Because it will help us to get the total H, the total thickness, because it will affect on the self weight and the dead load of the structure. So once we got the depth, okay, again, I just want to concentrate that the short span covers the effective depth. Okay, now we need to estimate the cover to steel reinforcement. The cover to the steel reinforcement, it depends on the larger of two values. The first value about durability, we have a table 3.3, page 206. Let's go and see this table. In this table, in the BS code, it will give you the nominal cover to all reinforcements. Okay, and depends on the exposure, mild exposure, moderate, severe, and so on. And also it depends on the concrete compressive strength that you are using. Starting from grade 30, it means 30 megapascal, going to 35 and to 50 megapascal. So it means how to use this one. Okay, if we assume that we have a moderate exposure, your structure in an area of a moderate condition, in this case, you will go take moderate and go horizontal. You will find that you cannot use a concrete strength of 30 megapascal in a moderate exposure. So the minimum concrete according to the BS in a moderate exposure equals 35. So in this case, how much it will be the cover? It will be 35 millimeter cover as it is given here. If you have, let's say, a severe exposure and you have a concrete strength of 45 megapascal, so you will go severe exposure with a 45, you will find that the cover is 30 millimeter. Okay, so based on the exposure and the concrete strength you are using, you will be able to get the minimum cover according to table 3.3, and called durability because it will, the cover helps to protect the steel against corrosion problems. Okay, how about the second method to get the cover? We get it also for fire resistant, because as you know, the function of the cover has two main functions. First one, to protect the steel reinforcement against environmental conditions. We get it from table 3.3. And also the second one is to protect the reinforcement against fire. And we get it from table 3.4, as we are going to see now. This table 3.4, it gives us cover for the reinforcement, but for different fire resistance per hour. So in the first column here, you have the fire resistance. You need your building to resist fire for 1 hour, for 1.5, for 2, until 4 hours. And here you have the cover based on the type of the structural element you have. You have for beams, you have for floors, for ribs, and for columns. So if we are talking about floors, slabs, you have case of simply supported and case of continuous. Okay, so let's say you have to resist the fire for 2 hours and you have a simply supported slab. So how much it will be the cover at this case? You will go for 2 hours, go horizontal, see the slabs, floors, you have simply supported will be 35 millimeter. If you have a fire resistance of 1 hour and you have a column, you need to design a column to resist a fire for 1 hour, you will go here 1 hour and you will go for columns, you will find it is 20 millimeter with some additional conditions can be seen here. You can do it yourself. So for the cover, we get the largest from the two values. Table 3.3, it will give you a value. Table 3.4, it gives you another value. And then you get the maximum, the larger of the two values. Then in this case, you can get the total depth or total height of the slab equals what? We call it H. The H equals the effective depth, which is from the compression side until the center line of the tension steel. You need to add the cover to the steel that we just calculated from table 3.3 and table 3.4. And then you have to add the diameter divided by 2, half of the diameter of the bar to get the total H of the slab, the total height of the slab. So the total height, which is this one, is H equals D, you get it from table 3.9, plus cover, the maximum of 3.3 and 3.4, plus phi over 2. And like for phi, we can assume the phi as 10 millimeter for our calculation, and you don't need to recalculate this one. If you design and you find a phi which is like 12 or 16 millimeter, no need to go and repeat this. So this is how to get the H, and by getting the H or the total height, we finish the first part about initial proportioning. Then we can move to a third step, which is the final proportioning. Final proportioning, it will include different parts. The first one, to get the loading on the slab. The main two loads on the slabs are dead loads and live loads. Dead loads, it will include the self-weight of the slab, and in this case for self-weight you need to get the H, which we got it on the second step in the previous slide, initial proportioning. If you have finishes, weight of partitions, weight of ceiling and services, all of this also will be considered as dead load. In addition to the dead load, we have also live load, or sometimes we call it imposed loads. We take it from the code, and it depends on the function of your building. Okay. Once you have the loads, you have to go to the structural analysis step to find the bending moment and shear forces on the slabs. After you get the bending moment and the shear force, we have to design for reinforcement. Calculation for reinforcement, we use section 3.4.44 in the BS code. You design for reinforcement in the short direction only if you are dealing with one-way solid slab, or you will design for both directions if you are designing for two-way solid slabs. Once we design for reinforcement, this is not the end. You need to make some checks to be sure that your structure is safe and can resist the loads and can satisfy the ultimate limit state and serviceability limit state. The first check here is a check for deflection. And checking for deflection, we use table 3.10, as you can see here. And it will come later after 2 slides. We'll talk in details about how to use this one to check our deflections. So once you check your deflection and you find it's safe, also we have to check for shear. And checking for shear, it is similar to the shear checks that we did for beams. But you have to keep in mind that no shear reinforcement in slabs should be provided if the H is less than or equals 200 millimeter. So if the height of the slab, the thickness of the slab is less than or equals 200 millimeter, you cannot add shear reinforcement. So what can you do if the shear is not safe? The only choice in this case to increase the H, to use more H, because if the H is less than 200, you cannot, it is not allowed by the code to add shear reinforcement. So what is table 3.8? Let's go and see this table. It is similar to the table used for beams. The main equations that we have it here for the VC, the shear carried by the concrete, equal 0.79 times between brackets 100 AS divided by BV times D to power 1/3 and times 400 over D to power 1/4 divided by gamma M. Gamma M, which is the material safety factor for shear, it is always taken as 1.25 according to the BS code. AS is the area of the tension steel reinforcement. BV is the width of 1 millimeter that we have it for slabs. D is the depth of the slab. Okay, but you have to keep in mind that this value here, 100 AS divided by BV times D, shouldn't be taken as greater than 3. So if it is less than 3, it is fine. Okay, you take it as it is. If it is greater than 3, take it as 3. Okay, so this value here, 100 AS divided by BV times D, the maximum value is 3. As you can see here from this table, the maximum is 3. Also for 400 over D shouldn't be taken as less than 1. And in slabs, of course, usually this one will be greater than 1. So don't worry about this part. Only you have to check about this one that shouldn't be greater than 3. And you should also keep in mind that this VC, the value of BC here, is calculated for concrete strength of 25 megapascal or less. So if you have a concrete strength of 30 megapascal or 40 megapascal, you have to multiply the values that you calculate from this table or from this equation by this factor here, FCU divided by 25 to power 1/3. So you multiply the values that you get from this table or from this equation by FCU divided by 25 to power 1/3. Okay, this is about the shear, and it will be more clear when we go and solve an example together. Okay, so we calculated reinforcement, checked for deflection, checked for shear, and it is safe. We have also to check for cracking. We have to be sure that the cracking will satisfy the serviceability requirements. The BS code satisfies the cracking procedure by controlling the area of the steel reinforcement and the spacing between the steel reinforcement. So it is not telling you you have to check the crack widths and you calculate the crack widths. It's some like difficult calculations. No, it is easier in the BS code, and many codes are using the same method now. So you have section 31253. It gives you the minimum percentage of reinforcement. So your reinforcement ratio should be greater or equal to the minimum reinforcement ratio. So this table 325, it will give you the minimum area of steel reinforcement for different cases. We are going to use this for beams, for slabs, but for slabs here, rectangulars, number C, rectangular sections in solid slabs, this minimum should be equal to this value. You have two values here, 0.24% and 0.13%. Depends on which type of steel you are using. If you are using high yield steel, 460 megapascal, so the minimum reinforcement ratio is 0.13%. If you are using mild steel, this minimum reinforcement ratio is 0.24%. Okay, so you have to control the crack widths by keeping your reinforcement greater than or equal to the minimum given by the code in table 325. How about the spacing? Also, again, you have to check about the spacing. In this clause 312.11.27 about slabs, it says in no case should the clear spacing between bars exceed the lesser of 3 times the effective depth or 750 millimeter. So the maximum spacing allowed by the code is 3 times the effective depth. So it's 3 times D, or 750 millimeter. When you choose the spacing between your reinforcement, you should be sure that it will be less than 3D and also less than 750 millimeter. So if you are satisfying the minimum area of steel reinforcement and the spacing between the reinforcement, you will be sure that your cracks will not exceed the crack width allowed by the code, and you'll have no problem in this cracking. After you finished all of this three, you finished all the design, but you have to show your design by drawings and detailing of the slabs. As you know, as an engineer, the drawings is the only way to communicate between engineers. So the engineer in the site, he will have a drawing. This drawing should have all details, so you can use this drawing to build the structure easily with all information given on that drawing. So for detailing, we can see here figure 325 in the code. This is showing where to cut the steel reinforcement, top steel reinforcement and bottom steel reinforcement. Maybe this one is not clear, but let's just to show you here a second one here for the bottom steel reinforcement in case, and top steel in case of continuous slabs and cantilevers. But I will give you this drawing here, it makes more clear. In a case of assembly supported slab, one span here, the code, it tells you at the middle of the slab, I need 100% of the reinforcement, because you know at the middle of the slab, you have a maximum positive moment, so you need more reinforcement. But close to the edge, the moment will be less. So you don't need to use all the reinforcements that you have it here. So what this drawing tells us, it tells us that the code like asked you or tell you you should use at least 40% of the steel reinforcement extend from the beginning to the end, and the remaining 60% you can cut them shorter, and this will give you the length here from this point to that point. This distance here, similar to this case, it is 0.1L, about the span divided by 10. So in a case of assembly supports, it tells you 40% will continue from the support to support. The remaining 60%, you can cut them. So if you, let's say you have 10 bars per meter, so you can make 4 bars long and 4 bars shorter. Usually you take 50-50, 50% longer, 50% shorter. In a case of continuous, as you know, for continuous, you have some positive moment at the middle of the spans or close to the middle, and at the supports above the beam, you will have negative. So in this case, it will require bottom steel reinforcement and top steel reinforcement. For the bottom steel, again, 40% will continue, and you can cut 60%. For this 60%, from the first support, it will be L/10, and from the middle support or interior support, it will be about 0.2L, or the span over 5 from the center line of the support. How about top steel reinforcement? Top steel reinforcement tells you like 50% should extend from the edge of the beam, not from the center line as in the case of bottom reinforcement. No, from the edge of the beam, it extends to 0.3 span. 30% of the span, which is, this is the span from center line to center line. So the top reinforcement, 50% at least should extend to 30%. Another 50% of the reinforcement should extend at least 0.15% of the L, and should be also greater than 40 times bar diameter. At the end support here, because there are some fixation or some continuity between the slab and the last beam here, so it will result in some smaller amount of bending moments here, negative bending moments. So you should have also some reinforcement. Usually this reinforcement will be taken as 50% of the main reinforcement. If you have here, let's say 10 bars per meter, you have to take here at least 5 bars per meter, and it should be greater than the minimum allowed by the code, which is 0.13% of the area of the concrete. Again, the distance here will be equal to C, 0.15 or 15% of the span, and not less than 45 times the bar diameter. Here about the anchorage or how to extend this bottom reinforcement here. You just stop it at the support, at the center line, or you extend. So the code is saying, no, this one should be extended. If the V is less than 0.5 VC, this is about the shear stress on the slab less than 50% of the shear carried by the concrete, this distance should be greater of BS over 3 or 30 millimeter. What is this BS? Is the thickness of the support. The width of the beam here, this is BS. So you divide this by 3, and this will be the extension here from the center line. It will extend to the greater of these two values. Okay, this is about detailing of reinforcement. Now, how to make the structural analysis of if you have a slab of continuous spans. Okay, for continuous spans, we have to use this table 312. For table 312, it tells you ultimate bending moment and shear forces in one-way spanning slabs. Okay, so you have values for shear, you have also values for moments. Okay, this will be more clear by seeing this drawing. Okay. Okay, what do we have here? We have the first row is for the bending moment. Okay, these values give you the bending moment values at different points of the slab. So at the first outer support here, in a case if you have assembly support at the beginning here, so the bending moment will be equal to 0. So this will be 0. At near the middle of the end span, this is the end span. So near the middle of the end span, the bending moment will be 0.086 FL. Okay, and we'll see what is this FL later. Okay, for continuous, I will keep it later. But let's go for at the first interior support, which is this one. How much is the bending moment? The bending moment will be a negative moment here, and the value will be minus, because negative moment, 0.086 FL. Then middle interior span, again, it is positive value less than the first span, and the value will be 0.063 FL. Okay. How about the case if you have the end support here has some continuity between the slab and the beam at this point? So it means I will have some negative moment here. And this is why we have this part in case of continuous. So you will have some negative moment at the beginning. It equals minus 0.04 FL. And also it will affect the positive moment. It will be reduced because you took some of the moment negative. So it will reduce the positive moment from 0.086 to 0.075 FL. But what is this F and what is this L? L is the span, this span and this span, third span, and so on. But how about F capital? F capital is the total design ultimate load. It means the ultimate load equals 1.4 dead load plus 1.6 live load. But this is capital, so it means the resultant of the load. So if you have a load here, which is a uniform load, so this uniform load, you get it at the ultimate, it means multiplied by 1.4 and 1.6 live load and dead load and live load. And you should multiply to get the resultant by multiplying this by the span. So you get a concentrated load here as will be a capital F. Then you will use this F, it will be multiplied by FL times this factor to get the bending moment values. Okay. Then the second part of this table, it gives us shear. Okay, so to get the shear, we get it from the second row. And again, to show this is showing the spans. So at the first support, here you have a shear of 0.4 F. No L anymore here because this F here equals the uniform load multiplied by the span as a concentrated load. So it is 0.4 times the concentrated load. 0.4 F. Then at the first interior support, it is 0.6 F. Then later on, it will be 0.5 F. In case, again, if you have a continuity here at the beginning, we have to use this table here, the value here. It will be just to change it for the red one. From 0.4, it will be 0.46 of the F. This is the only difference. So how to use this if you have a problem, or you have a slab, continuous one-way slab, and you have different loads here. So if you have a slab with a span L1 and a span L2, the first span is loaded by a uniform load called W1 kilonewton per meter. The second span has a load of W2 equal also kilonewton per meter. So what you should do, you should get the resultant of the first span, the resultant of the load on the second span. So we call it F1 equals W1 times L1. This is the F that we use it here in this equation. Then you will repeat this for the second span. So you will have F2, it equals W2 times L2. It will give you a force here as kilonewton here, as kilonewton here. Okay. Then we have to use this F to get the bending moment values. So from the table, the value here will be 0 at the near the middle of the first span will be 0.086 F1 times L1. Then here F2, and here also let's write this one. Okay, I forgot here to add this L2. Okay, so 0.063 F2 times L2. And how about the middle support here? Because in the middle support, you cannot say 0.086 FL, okay? Because you have F1 and F2 and L1 and L2. So here we get the average. So it will be 0.086 times F1 L1 plus F2 L2 divided by 2. So you get the average from both, and this will be the one that you take it to get the negative moment at the interior support here. Okay, then for the shear, we are going to do the same. You will use the values at the bottom here. So it will be 0.4 F1, then here 0.6 F1, then it will be 0.5 F2 and 0.5 F2 and so on. Okay, so in a case if you have a real problem with different spans, with different loads, the important thing here at the middle one, you get the average of F1 L1 plus F2 L2 divided by 2 multiplied by this factor here, which is 0.086. About checking deflection, how we check the deflection? Okay, as I told you, we have to use a table in the code. The deflections are important to be checked because if you have excessive deflection, it may cause damage of ceiling, finishes, or other architectural details. To avoid this, we have to use the minimum effective depth, which is the span divided by basic span to depth ratio from the table 3.9 multiplied by the modification factor. Let's remove this one. Okay. Then to do that, or to check the deflection, we have to get a value called modification factor. This modification factor we have to check. At the beginning, we assume modification factor 1.3, but now we need to check how much is this real modification factor after we make our calculation and we got a depth and total H of the slab. To do this, we get this modification factor from table 3.10, which is this table. In this table, you have a modification factor equal this value, 0.55 plus 477 minus Fs divided by 120 times 0.9 plus m over bd square, and this should be less than or equals to 2. Okay, we have some values here we need to know. What is the Fs? This is the stress in the tension steel, the stress in the bottom tension steel. How much is this stress, Fs? Also, what is m? M is the maximum positive moment, not negative moment, because the deflection will be at the span, not at the support. So this M here is the maximum positive moment. B, as you know, is 1000 millimeter for slabs, and D is the depth of the slab. Okay, so how to use this one? To use this one, we have to get the value of M over BD square, and we have to get the Fs. How much is this Fs? We get it from this equation here, according to the code. It equals 2 over 3 F yield times AS required divided by AS provided. AS required by design and the real area that you provided. times 1 divided by beta b, and beta b, this is something for redistribution, and we use it as 1 in this case. So to use this one, you need to get the fs. Once you get the fs, you put it here into this equation, then get m over bd square and you put it there. You substitute into the equation, get the modification factor. Okay, let's go back and see. So again, this is the m from the same equation that we just saw together. Okay, as I just explained, m here is maximum positive moment in the short span, because usually you have more moment in the short span, or always you will have more moment in the short span than in the long span, because it takes more amount of loads. Then to get the fs, we get it from this equation, as I just explained. As required, this is the area of reinforcement required at mid-span. As provided, area of reinforcement provided at the mid-span, and beta b is the ratio of mid-span moment after and before redistribution. And usually the code is not allowing to make redistribution if you are using the coefficients from the table to get the bending moment and the shear. Okay, once we got m, so we have to calculate something called limiting span to depth ratio. Okay, limiting span to depth ratio, it equals basic span to depth ratio from the code, the value that you get from the code, which was 20 in case of simply supported or 26 in case of continuous, multiplied by m. So the m that you calculated from the previous equation in the previous slide here. Okay, so you multiply this m by the basic ratio that you used at the beginning. So m multiplied by 20 or m multiplied by 26. Then we calculate the actual span to depth ratio, which is the short span divided by the actual depth. And then we compare this one to that one, the first one to the limiting one to the actual one. If the limiting span to depth ratio, the first value here, greater than the actual span to depth ratio, it means, okay, the deflection is safe. You can continue and you will not have any problem in the serviceability regarding deflection. If the limiting span to depth ratio was less than the actual span to depth ratio, it means it is not safe. Okay, it is unsafe. And the solution in this case to increase the depth, and in some cases also, if you cannot increase the depth, you can increase the reinforcement, because it will help to make the deflection more safe, because it will affect this value of fs. Okay, this is the end of our presentation today. The coming one, we are going to talk about a real example and how to solve a problem with simply supported one-way slab. And then we will have a second example about how to solve a continuous one-way slab. Thank you, and see you in a coming video.